Okay, so we're here on November 23rd, getting close to the end. 3 weeks. 3 weeks and one assignment away. So today we're going to talk about indicator random variables, which are a type of random variable, but to do a specific job. So they count things for us, which sometimes we want to count events instead of giving them a value. So then the values we give them are 0 or 1. I do want to address, let me see if I can, sorry, I gotta move stuff around a bit here. Okay, I do want to address assignment 3. So it was brought to my attention, who is it, Sam Haskins. So he noticed that the solution to question 4.4 was not correct. All right, so I posted a new solution. What happens is we introduced this thing called similarity between songs. So before it was original songs, and original songs all had uniform probability. And then I introduced this concept called similar songs, and then it was my intention that they had uniform probability, but I didn't say that. So then, of course, that means that according to the question, it's still the original songs that have uniform probability, which makes this a lot more difficult. So the original solution, which probably, if you went for help with the TAs, is probably the direction that they pushed you in, because that was, the solutions that I gave them at the time. So you could get full marks for the solution, but it's not correct. Because this assumes uniform probability of two similar songs. However, they're not uniform. You have to, each similar song forms a category, or each, there's all the different types of similarities form categories, and in those categories, there's a number of original songs. And the number of original songs, that forms an event, right? And then, so the number of original songs over the total sample space is the probability of a random song landing in that similarity bucket, right? And then you have to compute, well, over all the buckets, what is the probability that two songs land in the same bucket? So it turns out it was much more complicated. I actually do like this question, and I might reuse it on future assignments, but yeah. So if you attempted to do this correctly, I will give you 2 bonus marks, all right, just for understanding the problem. However, the TAs have started marking. I told them if, to look, if they remember, to go back and check or whatever, but if they miss your assignment, then email me if you think that you were marked incorrectly. So you get 2 bonus marks for even attempting this way, and then the usual 0, 1, or 2 for getting it correct, or sort of correct, or not correct at all. All right, but yeah. So that's assignment 3. Any questions before we get started? Okay, I guess one other thing I should mention is, so our, what is it, the 13th here is the exam, right? So that will be 25 multiple choice. It'll be a 2-hour exam, and I think it's at 7 p.m. Somebody's unmuted. I'm just going to mute you. Okay. All right. So let's get on with last class. We talked about. We did talk about this. We did this expected value problem. So we solved it for. Yeah. So we said basically any type of. We're going to review this again, actually, but any type of trial that has success with probability p and failure with probability 1 minus p. And when we do the trial until we achieve success, so we just keep trying over and over again. How many multiple choice? Were 25 multiple choice on the final. So the midterm was 17 and 80 minutes. The final is 25 and 120 minutes, plus, whatever, a little bit, so that just in case Brightspace is not responsive or whatever. Okay, so then the expected number of trials, if I'm doing an infinite number of trials until success with and success comes with probability p, then the expected number of trials is, of course, 1 over p. So for instance, if I flip a coin with probability 1/2, actually, sorry, I'm not set up properly here. All right. So if I flip a coin with probability 1/2, if I flip the coin until I get heads, flip until heads, then I would expect the number of flips equals 1 over the probability of success, which is 1 over 1/2, which is 2. So I would expect to flip the coin twice on average before I saw heads. That relates back to this question of the couple who was having children until they had a girl. Well, then the expected number of children is going to be 2, right? Because success comes with probability 1/2. So the expected number of children will be 2. And then we left off with the question, well, what happens if they have children until they have 2 girls? Well, we did this as well. 2 girls or 3 girls or whatever. Well, this is just a certain number of trials, and we can use linearity of expectation. So we could say that x1 is the number of children until the first girl, and x2 equals the number of children until the second girl. And then we could apply linearity of expectation, right? So E of x is the number of children, is the expected value of x1 plus the expected value of x2, and so that would be 2 plus 2. And then we could, so there would be 4 children on average if they had children until they had 2 girls. Of course, the same applies if they have children until they have 2 boys. So whatever your goal is, you are likely to have an equal number of girls and boys, right? From here, we can reverse engineer since we know there's exactly 2 girls. That means that the expected number of girls is 2, and then the expected number of boys is also 2. All right. So yeah, anyway, that was just the problem we left off with last class. This class, we will do some slightly different stuff. Okay, so today we're going to look, well, the problem that we're going to look at is going to apply Newton. So we're looking at not only indicator random variables, but a binomial probability distribution. So again, we have a probability P that is between 0 and 1. And we perform an experiment. We have success with probability P and failure with probability 1 minus P. So there's exactly 2 outcomes in our experiment. So for instance, if we have a coin, it comes up heads with probability P and tails with probability 1 minus P. So perhaps it's not a fair coin. Yeah, so then X is the number of trials. Then yeah, this is just a review. Sorry, this is just a review of what we did last class. Okay, so yeah, so for example, if we flip a coin with probability P equals 1/2, then the number of coin flips until heads comes up is 1 over P, which is 1 over 1/2, which is 1/2. On the other hand, or sorry, 2. On the other hand, if we play the lottery, and let's say we have a probability of 1 in a million of winning the jackpot, then on average, so we play the lottery, every week until we win. And then we do that a number of times, and we take the average number of days it takes until we win. Well, yeah, the average number of tickets would be 1 over P. So P is 1 over a million. So the expected number of tickets bought until we buy a winner is on average going to be 1 million. Right. So playing the lottery is, you're going to probably wait a long time. But of course, anything can happen. Okay. So that's just all last class review. Are there any questions on that? Okay. So now we're going to do a slightly different experiment. We're going to flip our coin that comes up heads with probability P and tails with probability 1 minus P. We're going to flip it n times. And Windows 11 is not deciding not to cooperate with me this morning. Great. So we're going to flip it n times, regardless of whether we come up heads or tails. Right. So then we're going to introduce a random variable x, and x is the number of times we flip heads out of n coin flips. Right. So yeah, we want to determine what is the expected value of x. Right. And yeah, so here we have 4 coin flips, and we see one of the coins comes up heads, for instance. So what's our intuition? If we flip the coin n times, yeah, well, spoiler alert. If we flip the coin n times and p is equal to 1/2, how many heads would we expect to see? How many times should it come up heads on average? So I flip a fair coin 4 times. How many heads do I expect to see? 2, yeah. So the average would be 2, right? Because we have probability 1/2. So we would expect to see about 2 out of 4 on average. So 1/2 of however many coin flips we had. If the probability of success was 1/3, well, then we might expect to see, that basically means that 1 out of 3 coin flips will be heads. So we would expect to see about 1/3 of our total coin flips coming up heads. And yeah, so if the probability was 1/4, then the expected number of heads that we flip would be about 1/4 times n. There's always at least one. Right? So that's what we think. That's sort of our intuition. But we can verify that with the tools that we've learned so far. Okay, so we flip heads with probability P. We flip tails with probability 1 minus P. We flip a coin n times, and we record the number of times it comes up heads. So what is the expected number of times it comes up heads? We think it's going to be the probability P times n. So what we will attempt first is we're going to solve this by iterating over the range of x, right? So we have our 2 expected value formulas. So we have the expected value of x is for all w in s. It should be omega, but McKeel would be disappointed in me for saying that. But yeah, so the probability of seeing w, or the probability that this is, probability that we come up w. So that's our first expression for expected value. But the other one we have is that we can iterate over the range of our random variable x. So if we group all of the terms in here that have the same value that is mapped by x, then we get, we take the value times the probability that x is equal to k. So those are our 2 forms for expected value. How come there's no limit on the top of the sum? Well, we don't know. This is sort of a generic way to apply it, right? Since we don't know how many elements are in S. We don't know, and yeah, I guess you could write it sort of like this, and then you can say W subscript I. But this is, I guess, a little more clear, right? We go through all of the elements in S. Here, I would have to now define WI, what that means and stuff. So that's essentially what it means. And here we just, yeah, when we write something like this where we only have something on the bottom, what it means is basically there's an implied for all here that we don't often put. basic. All right, other questions? Okay, so yeah, out of those two, we're going to use the one where we iterate over the range. And we will try to find our, the expected value that way. Okay, so k takes on all possible values of x. K is the range of x. So what are the different values that k can take? Well, if I flip a coin, here I flip a coin 4 times. If this came up tails, if they all came up tails, then my x would be 0, right? Which is also the same as saying k is equal to 0, since we have x equal to k. Right, so if we want to find the range of our random variable x, well, we know that it can be as low as 0, and then it can be as high as basically, well, if all of these were heads, I could flip all n coins to be heads, so it could be up to n. So x is somewhere in the range of 0 to n of integers. So those are the values that we want k to take on, and then we want to find the probability of each of those. Okay, so x can be 0 if all n flips come up tails, or x can be n if all flips come up heads. So we want to iterate over all possible values from 0 to n. Okay. So now we know the range that we want to iterate over, and now we want to find this probability here. So this is not going to be quite as easy. Now of course, this defines an event. To find the probability of an event, we have to sum up the probability of all of the outcomes in that event. So what are the possible outcomes and what are their probabilities for this event? So x equal to k, for instance, so here's our sample space. Our sample space is some series of n flips, where each flip can take on heads or tails. This is each value that x can take on is an event, and I want to sum up all of the probabilities of the elements in that subset. So we will look at an example for n equal to 4 and the event that x is equal to 2, so 2 heads were flipped. So we want to try and get some intuition into how we can compute this probability. Right, so all of the possible outcomes, well, we have heads, heads, tails, tails. We have heads, tails, heads, tails. We have heads, tails, tails, heads, tails, heads, heads, tails. So each of them has two of the coins that come up heads in each of these outcomes, right? So that's the definition of this event. So now, what is the probability of each of these? Well, so we know that, so let's take heads, heads, tails, tails. Before, when we computed that, we had p was equal to 1/2, and then 1 minus p was also equal to 1/2. But now actually heads has a different probability than tails, so we have to, so the probability that we get, and these coins are flipped, these are independent coin flips, as coin flips should be. So each head comes up with probability p. These are independent coin flips, so we would say that the probability of heads and tails equals the product of the probability. So the probability of heads times the probability of heads times the probability of tails times the probability of tails. Okay, so that is, by the definition of independent events. So then the probability of this is, well, we know this is p, we know this is p, we know this is 1 minus p, and we know this is 1 minus p. So then the probability of this event, or this outcome, sorry, is p times p times 1 minus p times 1 minus p. Yeah, so that would be, I think I did this in a different order actually, but yeah, let's, first of all, we will list out all of the possible outcomes, and then, yeah. So here I have heads, heads, probability of tails, probability of tails. All right, so now for this guy, I have heads with probability p, and then tails with probability 1 minus p, and then heads with probability p, and then tails with probability 1 minus p. Right, now for the next guy, I have heads probability p, 2 tails probability 1 minus p and 1 minus p, and then heads with probability p. So I get p times 1 minus p times 1 minus p times p. Right, and we can keep going that way. So here is 1 minus p for the tails times p for the heads times p for the heads times 1 minus p for the tails, etc. No, I did this one in different order. Yeah, sorry, this should be at the bottom and this should be up here. But regardless, I think you get the idea. Right, so is there questions on that? Everybody understands how to compute the probability of 4 independent coin flips, hopefully, or questions? Okay, so then if we gather the like terms, these are, multiplication is, it's associative and it is commutative. So we can gather all of our p's together, p squared, and the 1 minus p's together, we get 1 minus p squared. And in fact, if we look at all of them, they all evaluate to the same thing. So p squared times 1 minus p squared, which is good that we have. So in some sense, this is going to work because the probability is all the same here. So if we gather all of these terms together, all of the terms that have the same value, they also have the same probability. That's going to make our life a lot easier. Okay, so we sum up all of the probabilities in an event. We have, this is the event, this is the subset. There are 1, 2, 3, 4, 5, 6 outcomes in that event. Each of them has a probability of p squared times 1 minus p squared. So then, yeah, the probability that x is equal to 2 is 6 times p squared times 1 minus p squared. But of course, another way to look at it is, how did we get this value 6? Well, we have 4 coin flips, and we said 2 of those 4 coin flips are going to be heads. So we want to count all of the ways that we can have 2 coin flips come up heads out of 4 flips total. That is 4 choose 2, right? So then that's equal to 4 choose 2 times p squared times 1 minus p squared. And, perhaps you might notice that this is starting to look like a little binomial. All right. Questions? Okay, so yeah, in general, so this is what it looks like for x equal to 2. If we want to generalize that for n coin flips, so this is here we have n equal to 4. But if we want to find for n coin flips in general, where k of those coin flips come up heads, in other words, we're going to choose k out of the n possible coin flips to come up heads, then that's going to be n choose k in general. So this 4 choose 2 will be n choose k. And then each of these has, well, we've chosen k of these, k out of n coin flips come up heads. Which means that the other n minus k coin flips our tails. Right? All of these coin flips are independent. They come up heads with probability P. So we have P times P times P, K times. And then that is times, that is times 1 minus P, 1 minus P, 1 minus P. That is N minus K times. So in other words, we can rewrite all of that as P to the K times 1 minus P to the N minus K. So the probability of each of the events where K out of N heads are showing is the probability that is P to the K times 1 minus P to the N minus K. I think I have to, since my bottom taskbar won't go away, I have to manually erase all this. Yeah, so then the probability of this event, X equal to K, which is, in other words, I have N coin flips and K of them came up heads, is N choose K times P to the power K times 1 minus P to the N minus K. Right? And this is, of course, looking a lot like Newton at this point. All right, questions on that? Okay, so we have our probability for each individual event. While we want to sum up over all of the events, X equal to K. So if we rewrite our expression here, substituting this in for this, we get the expected value of X is equal to the sum from K equals 0 to N of K times N choose K times P to the K times 1 minus P to the N minus K. All right. And then apparently all of this should simplify to P times N. So that is we want to show that this is actually equal to P times N. So this, as we will notice, it kind of looks like that, except for we have this extra K term here, right? This is actually, and we've seen something similar to this before when we were looking at infinite series. There was a K there that we hadn't seen before, but we could introduce it by taking the derivative of the expression that we did know with respect to X at the time. So if we took the K out, this would look very familiar. However, it would look like this. However, we do have a K in there, so we want to take this and introduce this K term. And we're going to use the same technique as before. We're going to take the derivative. So how do we introduce a K term? Well, if I have some, for instance, if I took the derivative, so Y is a variable that's raised to the power K. So if I took the derivative with respect to Y, so d of dy of y to the k is equal to k times y to the k minus 1. Again, hopefully you can follow along with this, but you're not expected to do derivatives, well, maybe some simple derivatives, but nothing too complex on the final. Okay, so if we take the derivative of this with respect to y, so we have this general form, we want to get to a general form that looks something like this, right? So here we have, this would be x is equal to 1 minus p and y is equal to p. Right, so we want something that looks like this. If we take the derivative with respect to y, well, this is just a bunch of, so we're summing up a bunch of terms. So for each individual term, we have xn minus k, y to the k. So if we take the derivative with respect to y, we get n to the k. So k, this k comes down, times x to the n minus k times y to the k minus 1. Right? And then if we do that over all of these individual terms, then we can just rewrite our summation with this instead of this. So yeah, the right-hand side is looking like this. And then we want to take the, we have the left-hand side, we want to take the derivative with with respect to y. So here we want to, again, we take down the n, and then we have n minus 1 here. So we have n times x plus y to the n minus 1 on the left-hand side. So this is almost looking like what we want, except we have a k minus 1 here, which is a bit awkward because k starts at 0. So it would be nice if we can get this back to k. Of course, there's an easy way to do that if I multiply both sides by y. So I have this expression now. I want to get to y to the power k. So I'm going to multiply both sides by y. And now I have this y is multiplied by every term in this series. So I get k equals 0 to n of k times n choose k, x to the n minus k, y to the k is equal to n times y times x plus y to the n minus 1. All right. So we have a closed form that resembles the thing that we wanted to prove, or find a closed form, which is right here. All right. Questions on that? No, it's a lot for 8:30 in the morning. Okay. So this is honestly, this is useful for understanding. It's a good review of binomial theorem and useful for understanding it. But when we're done all this, we're going to do it the easy way with linearity of expectation, which is what you should remember. And one of the reasons why we show you this, even though we could do it with linearity of expectation, is to see how powerful linearity of expectation is. It really is. It's a shortcut to determining expected values. It's very, very useful. Okay. So now we have this expression. We have this expression in our toolbox that we can use. We want to solve this expression. So now we're just going to substitute y or p in for y and 1 minus p in for x in this closed form. All right, so that is equal to, x is equal to 1 minus p and y is equal to p. So if I take this n times y times x plus y to the n minus 1, that is equal to this, but now I'm going to substitute for y. I will put p. X is 1 minus p, and y is p, and this is to the n minus 1. All right, so this here is equal to this. The minus p and the plus p cancel out. I end up with n times p times 1 to the n minus 1. So 1 to any exponent is, of course, simply 1. So we end up with n times p, which is what our intuition told us should be happening. So, yeah. All right. Questions on that? Okie dokie. So is there an easier way than Newton's binomial theorem? Newton's binomial theorem is very useful, but very awkward to use. So there's a much easier way to prove it is by defining what we call, we're going to make some new random variables. These are called indicator random variables. So these new random variables will be x1 through xn, and we'll say that for a given xi is equal to 1 if the ith flip comes up heads, or 0 if the ith flip comes up tails. Right, so this is going to indicate to us whether or not heads came up. So now, if we want to count the number of heads, x is the random variable, the number of heads. So if we want to count the number of heads, we can simply add up all of these indicator random variables, right? Since, each one of these heads will correspond to a 1. Now, if we want to find the expected value of x, that is, of course, the expected value of the sum of these random variables. Well, that is, of course, equal to the sum of the expected values of those random variables, right? That is the linearity of expectation. Okay, so now we have an expression that is the sum of a bunch of random variables. Each of these random variables defines, each of these values defines an event. So xi equal to 1 is the event the ith flip is heads. Xi equal to 0 is the event the ith flip is tails. So those are, of course, each of these are independent. So yeah, the probability, the expected value of E for each of our indicator random variables is the, I'm going to iterate over the range. So the range is actually 0 or 1. So it's the 0 times the probability that xi is equal to 0 times 1 times the probability that xi is equal to 1. Right? So if I expand out this expression for expected value for this random variable xi, I get this. Of course, 0 times anything is 0, so we don't care about this term, right? That just disappears. 1 times anything is just the thing itself, so this actually evaluates down to the expected value of my indicator random variable xi is simply the probability of that event happening, right? In this case, the probability that xi is equal to 1, or which is the probability the ith flip is heads. So indicator random variables are very, very nice in terms of when we iterate over the range in order to compute them. The 0 event disappears because it's 0 times whatever probability. And the thing that we're trying to indicate is happening simply evaluates to the probability that that thing happens. All right. Questions on that? Everybody's following. Okay. So yes, the probability that xi is equal to 1 is simply that the ith flip is heads. We know that probability. We have it here. All of these coin flips are independent, so nothing will impact it. None of the other coin flips will impact it. So then the expected value of xi is simply p, which is, nice. So we have the expected value of any of our individual indicator random variables as p. We have the expected value of x is the sum of the expected values of all these indicator random variables. So that is equal to p plus p plus p, all of this n times. Right, so that is equal to n times p. So something that was very, very difficult, well, we had to use Newton. I suppose it's not that difficult if you use Newton every day, but we had to use the binomial theorem, and we had to take a derivative, and then we had to evaluate that. Or we simply take the, the sum of the expected values of these indicator random variables. The indicator random variables are very simple to compute. And then, then finding the expected value of x is quite easy. Right, so yeah, these are, as I've said multiple times already, indicator random variables. So they indicate whether an event has happened or not. And then we use them traditionally to count how many times an event happens. Okay, questions on that? All right, we'll look at some more indicator random variables. So let's say we have a random bit string, or any bit string, right? So we'll say that a block of ones is a consecutive sequence of ones with zeros or nothing on either side. So this, this one here, nope, that's not what I wanted. Sorry, I went to the end here. All right, so this one here is a block because it has a 0 on this side and a 0 on this side, and everything in between those zeros are ones. This here is a block, again, because it is in some sense bracketed by 2 zeros. This is also a block because I have a 0 on the left and then I have nothing on the right, which is fine, right? So that's 0 or nothing on either side. That's how we define a block in our bit string. And a bit string is, of course, simply a string of zeros and ones. Okay. So yeah, the definition, a maximal contiguous subsequence of ones, right? So what that means is there are no zeros in here, and I take the biggest subsequence of this that I can that still fits this definition of a block. Okay, so then the question is, given a random bit string of length n, so each bit comes up 0 with probability 1/2 or 1 with probability 1/2. We want to count the number of blocks in our random bit string. Okay. All right. So everybody understand the problem and what we're trying to do? Of course, we want to get an expected value of this, which doesn't look that easy because let's say that we wanted to iterate over the range of our random variable x. So let's look at the event x is equal to 3, right? For some, probably, I don't know, 10, some length 10 bit string, random bit string. So how can we compute it? Well, if we iterate over all possible values, this is our expression for expected value. The possible values for k, well, I can have all zeros, right? And then the number of blocks is equal to 0. So x is equal to 0. I can have something like this where I have 3. But then the maximum number of blocks I can have would be, well, each individual one by itself is a block. So I could have something that looks like this. Right. So if I start with 1 and then 0, 1, 0, 1, 0, 1, then I have basically the maximum number of these blocks that I can have. And then depending on whether it's even or not, I end with either a 1 or a 0. Right. So in this case, the largest number of blocks I can have is the ceiling of n over 2. So it's either, n over 2 or n over 2. It's either n over 2 or n plus 1 over 2. Sorry, I almost said n over 2 plus 1. All right. Okay, so then the range of k is k from 0 up to the ceiling of n over 2. All right, so what is the probability that x is equal to k? Well, we can take, for example, x equal to 3. So this is a random bit string with 3 blocks in it, or just a bit string with 3 blocks. This is also a bit string with 3 blocks in it. This is also a bit string with 3 blocks in it. So we have 1, 2, 3 here. We have 1, 2, 3 here. 1, 2, 3 here. These all look very different, and it's not hard to think of other examples. I could, in fact, change this to a 1. That's another bit string with 3 blocks. I could change that to a 1. Yeah, there's all kinds of examples. And in fact, if we wanted to compute the probability the old-fashioned way by counting, it seems like we're going to have a lot to count. So trying to count bit strings of length n with exactly 3 blocks is a lot of work. So what we want to do is we want to try and be clever about this. So we want to, of course, we're going to try and use indicator random variables, but we're going to try and do it in a way that we have to choose them or how we represent them or what we are counting correctly. Okay, so x is the number of blocks. So one thing we might take note of is that each block has a leftmost one, right? So this block, the leftmost one is simply the block itself. For our next block, the leftmost one is here. For this block, the leftmost one is there. So each of the individual blocks must have a leftmost one because by definition, the block to the left of that would be either 0 or nothing, right? Okay, so now maybe we can count, we can say that x being the number of blocks is the same as x being the number of starting positions for each block. So yeah, now instead of counting, trying to figure out all of the ways that we can have, different, I have a block starting at location 4, and I can try and count all the different lengths that it could possibly have. And then I have to, take into consideration that there's another block to my right. But here all I'm going to do is look at the starting position. I don't care about the length. I don't care about anything else. I'm just going to count the number of starting positions I would expect to see. So instead of explicitly counting the blocks, we're going to count each position that is a leftmost one of a block, right? So we are going to define indicator random variables x1 through xn. This should be, well, I should be using some other variable here. Oh, actually, no, sorry, xn, that's right. So our bit strings are length n. So a block can start at location 1, it can start at location 2, location 3. We can even have a single block start at location n. So yeah, we need indicator random variables for each location in our bit string. So the indicator random variable xi is equal to 1 if a block starts at location I and 0 otherwise. Okay, so now if we want to count x being the number of blocks, which is also equal to the number of starting positions, then x is equal to x1 plus x2 plus x3 up to xn, right? So for example, if we look at the one that we have defined here, our indicator random variables, well, the first x1 would be 0 because there's a 0 here. X2 would be 1 because there's a 1 here. X3 would be 0 because there's a 0. X4 would be 1 because it's the start of a block, so that would be 1. X5 now would be 0 because this is not the start of a block. X6 is not the start, X7 is not the start, X8 is not the start, X9 is the start, so we would have a 1 here, and then a 0 for X10. All right, so that's how our random variable X and our indicator random variables X1 through Xn will work together to count the number of blocks in our bit string. All right. Questions on that? All right. And yeah, so here's the corresponding, this is where the bit string starts, and here's the corresponding one where it starts. Okay. So we have X is equal to X1 up to Xn, which means the expected value of X is equal to the expected value of X1 plus, the sum of X1 through Xn, which means that the expected value of a sum of random variables is equal to the sum of the expected values of those random variables. So now we have an expression, and now we know that these are indicator random variables. So of course, indicator random variables are, whether or not they're simple to compute the probability with, the expression for them is quite simple, right? So I want the expected value of xi is equal to 0 times the probability that xi is equal to 0, right? For this, or 1 times the probability that xi is equal to 1. So then that, of course, simplifies to the expected value of xi is equal to the probability that the xi is equal to 1. So what is this probability? If we can determine that correctly, then this will be easy to calculate. Okay, so for all values from 2 up to n, xi is equal to 1. Well, what does that mean? So that means I start a block at the ith position. That means that to the left, right? So since we're starting at position 2, to the left of position I must be a 0. Since this starts a block, the position to the left-hand side must be 0. So in order for xi to be equal to 1, we have 2 coin flips, or 2 of these, if we define these random bits by coin flips, then we have 2 of these coin flips to determine. Right, so 2 coin flips will determine whether I is the start of a new block or not. We don't really care what's to the right of it. Okay, does that make sense? Why is the range of I starting at 2? We're just breaking it down into 2 different cases. We're going to look at the case where a block starts in the first location as well. But that's sort of separate because the probability of that will be a little bit different. That's all. So we're looking at all possible values starting at 2. We're going to look at I equal to 1 afterwards. Okay, so then we can determine this probability pretty easily. So each bit is a 0 with probability 1/2 and a 1 with probability 1/2. So each of these are independent. So this has probability 1/2, this is probability 1/2, and they're independent. So the probability that xi is equal to 1 is 1/2 times 1/2, which is equal to 1/4. So yeah, we know the value of this, or the expected value of this random variable xi. For I equal to 1, well, x1 is equal to 1 if and only if the first location is 1, right? It doesn't matter what comes after. It could be a 0 here, it could be a 1. But in either case, this is the start of a new block. So now we only have one location to determine the value of this random variable. Of course, this is 1 with a probability 1/2. So E of x1 is equal to 1/2. Okay, so we know now the value of all of our indicator random variables, or rather, sorry, the expected value of all of our indicator random variables. So now we can determine the expected value of x, which is the number of blocks. So yes, E of x is equal to the expected value of the sum of x1 through xn, which is equal to the sum of the expected values of x1 through xn. And x1 we know is 1/2, and all of the rest of these are 1/4. So we have 1/2 here, and then n minus 1 of these 1/4 terms. So we have 1/2 plus n minus 1 times 1/4, which is equal to 2. Yeah, if we put the whole thing over 4, then this becomes 2/4. Then we have a common denominator, and we have 2 plus n minus 1 over 4, which is n plus 1 over 4. All right, and yeah, so that is, I mean, that's pretty impressive that we can actually figure out on average how many blocks of ones there would be, because I mean, this is a mess. If we tried to count all this, all the ways that we can have 3 blocks is a complete mess. So using linearity of expectation and choosing our random variables correctly, we come up with something very easy. So yeah, linearity of expectation is quite impressive in that way. All right, questions, comments? Yeah, so definitely. Okay, so we know that, yeah, so to determine the expected value of a random variable, we're going to, and in particular for indicator random variables, we're going to iterate over the range. Well, the range of an indicator random variable is always simply 2 values, right? 0 and 1. So this is our old friend E of x equals the sum for all k of k times the probability x equal to k. So this is the thing that we're applying. However, here k is only 0 and 1. So I have my 0 term here and my 1 term here. Now this 0 times anything is of course 0. So then the expected value of any indicator random variable is simply equal to the probability that that indicator random variable is equal to 1, which, and then that corresponds to whatever event we said. Here it is, a block starts at I. So block starts at I. Now, what needs to happen for a block to start with I? Well, for all of these locations where, for an I that's not equal to the first location, so the first location is special, well, xi is equal to 1 if and only if location I minus 1 has a 0 and I has a 1, right? So in order for a block to start at any given location, that has to be preceded by a 0, right? Because if a block starts at 4, then a block cannot start at 5. So that means if I had a block start at 5, this would have to be 0 instead of 1. So in order for xi to be equal to 1, I need a 0 in the previous location and a 1 in location I. And then what happens in I plus 1? Well, if I have a 1 here, that's fine. This is still the start, this is still the start of a new block. Or if I have a 0 here, this is also still the start of a new block. So I don't care what happens in I plus 1. What I need to have happen is 0 before it and then 1 at that location. This has a probability of 1/2 of coming up 0 in a random bit string. This has probability 1/2 of coming up 1 in a random bit string. These are 2 independent events. So the probability of both of them happening is equal to the product of the probability, which is 1/4. right? So all I'm doing is I'm saying that for this event to happen, I need these two events to happen. I know the probability of those two events, so I can determine the probability of this event, right? And so that's what I do. Now for the other case where I is equal to 1, that means that if xi is equal to 1, that means I need a 1 in the first location. And then after that, what happens in location 2? Well, if it's a 0, then this is still the start of a new block. And if it's a 1, well, this is still the start of a new block. So whatever happens afterwards, I don't care. All I care is that this has 1. So the event that a block starts in location 1, that happens if and only if the first bit is a 1, which happens with probability 1/2. So the probability of this event is equal to the probability of this event, which is equal to 1/2. And so now I have my first random variable has a value of 1/2. Since for an indicator random variable, the expected value is simply the probability of whatever event is defined here, the probability of it happening. All right, so questions on that? Does that help at all?
I got a quick little question.
Yep.
So everything you just said, I follow on the slide, and then on the next one, if you don't mind.
Yeah.
Up to the 1/4 plus 1/4 plus 1/4, etc. Oh, okay, so that's n minus 1 times.
Yes, n minus 1 here. Yeah.
So the first character or the first position, and then all the remaining positions.
Yeah, this is sorry, this is x1 and this is x2, x3 up to, or these should be e of x2, a of x3, etc. Exactly.
Okay, that was one of my questions then. So the second one then would be for each of these probabilities. I understand how you got them. I guess because the events are independent, we don't have to worry about the probabilities. It's going to be hard for me to say this.
Are the events independent though? So
no, but for each selection of like, yeah, I did pick my words good there.
So that is maybe, I don't know, maybe your question is something that we're going to address shortly, but I mean, so determining the probability that this happens is pretty straightforward, right? I mean, you see that it's simply, but as you may or may not be referring to, that these indicator random variables are not independent, right? Like if I know, is that what you're getting to?
I think so, yeah, because we have 1/4 plus 1/4, but that kind of requires that the previous position is a 0.
Right, exactly. So this can't be a 1 if this one is a 0.
Yeah.
Or sorry, if this one is a 1, I mean. Yeah, so then this must be 0. So you're right, they are dependent. So that's sort of the next idea that we're going to address. Yeah.
I like what I see. I just felt like we were playing fast and loose, and I didn't know if I was interpreting things wrong.
No, that's a good observation. That's a very good observation. Because yeah, intuitively, you're thinking, well, what can I say about this value? Or if I say something about this value, then I must say something about this value, right? There is a dependence. So yeah, these are not independent random variables. So if I have a block that starts at 2, I cannot have a block that starts at 3. So x3, if x2 is equal to 1, x3 must be equal to 0. So these are not independent random variables. Oddly enough, though, we don't need, linearity of expectation does not need independent random variables. So when we proved linearity of expectation, we did not use independence of these random variables. we simply, did the algebra and it worked out. So that means, this linearity of expectation does not require independent random variables, which is kind of weird and counterintuitive, right? But that's one of the things that makes it most powerful, is that, these random variables are not independent, but I can still use this linearity of expectation to compute the expected value of X. Yeah, that's actually, really good observation. And the explanation for it is that, well, we just didn't use independence when we proved linearity of expectation, so it doesn't have to be independent. All right. Other questions? How does this take care of bit strings with more than one block? Well, we just say on average, we expect to have about, basically n over, 1/4 n will be blocks, right? So I'm worried about bit strings and alpha greater than 1 or 0. Yeah. Well, so the process is straightforward. We're going to practice it. We're going to practice it a lot. Of course, things can get more complicated than this. How does this take care of bit strings with more than one block? Yeah, so I'm not sure what you mean here. So what we're saying here is basically, if I take all the possible random bit strings, then on average, they have n plus 1 over 4 blocks. That's basically what this is saying, on average, which is, I don't know if I answered your question or the question that was before that. I'm not sure what you're asking, but yeah. So anyway, linearity of expectation, powerful as long as you remember sort of, you define your indicator random variables correctly, and then remember how to compute the expected value. Okay. So that's it for this. So we have about 10 minutes left. So I have a couple exercises that we can go over. I don't want to start the next set of slides. I can, I guess, but I thought it might be interesting to look at some of the more interesting exercises from the textbook. And just to practice expected value and see how it's applied in a variety of settings. This one might be a good one to do because this is sort of 6.19, because it's sort of related to the assignment question. How much of the assignment can we do at this point? I would say most of it. I would have to take a look, but you can. So the last part of the class is really, a lot of the technical things that you need to know, but now the remaining classes will be putting them into practice in more interesting settings, right? And maybe learning a couple of other tricks. But in terms of learning new topics, indicator random variables and expected value and random variables is basically going to be all of the rest of the class until the last couple of lectures, but that material is not on the assignment. So at this point, you can try everything on the assignment. You may need to learn 1 or 2 more tricks, but you have the tools, I guess, at this point to attempt everything. There's nothing past expected value on this assignment. All right. Okay, let's take a look at this question. Let me actually pull this over here. So this is somewhat related to something on the assignment where we roll the dice, we have to find, so of course one of the questions is rolling 4 dice, and then given that we subtract the lowest one and then take the 3 highest, and then we put a lower bound on the expected value of that. So this is kind of similar to one of the parts of that question where this is, I want to find the expected value of X, which is the largest value in these 5 rolls, right? So I'm going to roll a fair 6-sided die 5 times. Each of these rolls are independent. Let's get a little bigger. And then the random variable X is the largest value in these 5 rolls. Okay, so I'm going to show you, I guess, we will start to do the really difficult approach, and then I'll show you how to do the simpler approach. So the hint is, what are the possible values for X, and what is the probability that X is equal to K? So if I have 5 dice rolls, then it's possible that they all come up 1, right? So we can have X equal to 1. It's possible that the largest value, that all of them are 2 and under, so I can have X equal to 2. And basically X can take on all values from 1 to 6. Right, so my random variable X can take on all of these values. So now if I wanted to iterate over the range to find my expected value, so yeah, this would be the expected value of X is equal to all values in the range of X times the probability that X is equal to K. So that's fairly straightforward. Determining the probability that X is equal to K may be a little bit less straightforward. So what is the probability that X is equal to K? Let's, for example, take, what is the probability that X is equal to 3? So that means the highest roll is 3 out of my 5 dice. So yeah, this is the event. Highest of 5 dice is 3. So how many ways, if we were going to, let's say, count the number of elements in this event, so how many would we be counting? Well, let's say that, so we know the highest is 3, so at least one of them must be 3, right? So we would say that, let's take I is equal to 1 up to 5. So then we will have the event. We can break this down into a bunch of sub-events. That is, 1 die is 3, 4 dice are less than 3. So that's one of the ways that this can happen. We also have the event 2 dice are 3, and 3 dice are less than 3. Then we have 3 dice are 3, and 2 dice are strictly less than 3. Right, so we can break this event down into a bunch of disjoint events that, and if I take the union of these disjoint events, it's equal to this event. Okay, so then if I iterate from I equals 1 to 5, I is going to take on these values here. So now if I count the number of ways that can happen, well, if I have 1 die out of 5, that is a 3. That can happen 5 choose I ways. And then the other 4 dice are less than 3. Well, that is, 5 minus, so each of them can take on the values of 1 or 2. So if this is, 1 or 2, so there's 2 possible values, and there are 4 dice, or in general 5 minus I dice that can take on these values. So the number of outcomes in this event, X equal to 3, So the number of ways that I can roll the dice such that the highest value is 3 is equal to this expression. And then that's kind of nasty because now I have to also, k is equal to 1 from 1 to 6. So I have these nested summations. So yeah, this is a valid way to do it, and you can apply then Newton's binomial theorem. Where did the 2 come from? So I'm saying the probability that x is equal to 3, right? So that means that the highest of 5 dice is 3. And if I say 1 die is equal to 3, then the other 4 dice must be either 1 or 2, right? So there's 2 possible values that they can take. Simply because I'm saying that this event is that the highest die roll was 3. Okay, so that's where this 2 comes from, because I have 2 choices for the value of that die roll. Okay, so this is a mess. We could do this. We don't want to do this. All right, so let's start over from this part here. We're going to break down this. Well, let's again look at this one and say, well, I can say that this event x equal to 3, which means that the highest die is 3. Well, that is equal to, if I take a superset of that, I can say that this is a subset of all dice are 3 or less, right? So if all dice are 3 or less, that includes all of the ones where the highest die is 3, right? So that makes sense, hopefully. Does that make sense to everybody? So now I want to find, well, I want to find the subset of this where all dice are 3 or less, but at least one of them is a 3, right? So what I'm going to say is that, well, yeah, I'm going to take the event that all dice are 2 or less, right? And I'll see that actually this is a subset of this as well. This is a subset of all dice are 3 or less. Less than or equal to 3. However, if I subtract all of these events, all of the possible die rolls from all of these possible die rolls, then I'm left with only the events where all dice are 3 or less, and at least one of them is a 3, right? So this includes, so for instance, all dice are 3 or less, I could have the 2, 2, 2, 1, 2. I have this event. But that is not a part of this subset where the highest die is a 3. However, this is part of this one and this one. So if I subtract all of these from all of these, then I end up with all of these, right? So then if I define an event, AI is equal to all dice are I or less, then I could say the event that x is equal to 3 is equal to A3 minus A2. All right, so then all dice are 3 or less, that's easy to count, right? So if I just need to, if I want to count this, I can count these 2. So the event all dice are I or less, that is equal to simply each die can take on the numbers from 1 to I. There's 5 dice. So there are I to the 5 of those. All right. So that means if I want to compute my expected value now, if I take this expression the probability that x is equal to k is equal to all possible die rolls. The size of my set, the highest die is k, which I can compute over all dice rolls. So this is, k times ak minus ak minus 1, which is simply, this is the same as the event x is equal to k, and that's over 6 to the power 5. So this is all possible dice rolls. Okay, so the expected value of this, I can compute the hard way, or sort of this easy, more intuitive way. This is equal to k times, I to the 5th minus I minus 1 to the 5th over 6 to the 5th. Sorry, not I, but k. Right, and then I can take the sum of k equals 1 to 6, put it in Wolfram alpha. Where is that? And yeah, I get basically the sum of k equals 1 to 6 of k, so this is the value. And then for some reason there we go. K, which is the value of k to the 5th minus k minus 1 to the 5th, over 6 to the 5th, which is 14,077 over 2592. And if we look, that is exactly what we're supposed to get. Is the right one the subset? On this part here, you mean?
I was just talking about if you scroll down a little bit.
Yep. Oh, down here.
Yeah, like with the words, like the subset words. Yeah, so the highest die is 3 is a subset of all dice are less,
Or 3 or
3
less.
or less. Wouldn't it be the other way, since the highest die being 3? Does that?
Well, the highest die is 3 is, so all dice are 3 or less includes this guy, right? But
Yes.
this set does not include this one.
Oh, okay.
So yeah, this set includes, or sorry, this set includes this set plus all dice are 2 or less.
Oh, okay. Yes. Okay, I understand now. Thank you.
Yeah, no problem. All right, we went a little over time on that, and yeah, I was a little bit rushed, but this is actually, if you go back to question on assignment 3, there's the solution to question, I think it's 8 or something. One of the solutions there explains this also, but I thought it would be a good time to sort of walk through it again. Anyway, all right, that's it for today. Sorry for going a little bit long. I can answer any questions, but otherwise I will see you guys on Thursday.